Great. Jim, happy Mars Day.
Yes, indeed. We're really excited about having the opportunity to come and talk about one of my favorite planets, the planet Mars.
Well, are you allowed to have a favorite? Because as NASA chief scientist and planetary scientist, are you allowed to have a favorite planet, or do you have to remain neutral and unbiased at all
That's
times?
a really good question. When I was head of planetary science, I gave a lot of public talks. I would have kids come up to the microphone. The first thing they'd ask me is, what is my favorite planet?
Yeah.
And as head of planetary science, my response was obvious. I love all my children equally.
Exactly. That's very good. Apart from Pluto, which we kind of forget about. We don't really talk about Pluto anymore.
Well, Pluto is just absolutely a mind-blowing object. I mean, when you think about it, it's much smaller than the moon, but yet it has its own atmosphere.
Yeah.
Complex organics are broken up and combined in the atmosphere to strings that we call tholins. They get so heavy, they fall. Those tholins we can make in the laboratory, they are red. So in certain places on the Mars, you could stand and it would be snowing red tholins. I mean, can you imagine that?
Wait, actually on Pluto?
On Pluto.
See, this is the thing. As a planetary scientist, every single planet just has these fascinating facts.
It does.
You've got to have well, presumably you worked on New Horizons. You must have worked on that particular project.
I did.
Which visited Pluto. I mean, I'm not going to sort of withholding your age. You've been at NASA for quite a long time. So you've kind of witnessed this great revolution in planetary exploration from,
yes.
I don't know, what was the first one you worked on?
Well,
you were post-Viking, weren't you? You must have been after Viking.
Oh yeah, post-Viking. So it turns out when I was at the University of Iowa, this is where I really got excited about observing the solar system and beyond from spacecraft. You know, I got so excited about astronomy in high school. I worked at an observatory. You know, so when I went to the University of Iowa, I knew exactly what I wanted to do, and that was to get involved in astronomy. So Van Allen was there, and they were on like their 50th spacecraft. Okay, so I got involved right away in testing and helping assemble instruments for a spacecraft. So my very first one was Hawkeye. Now that's a very small spacecraft. You can almost put your arms around it. And it orbits the Earth in a highly elliptical orbit, and it actually goes out in the solar wind and then over the polar cap and then very close to the Earth. And it's a beautiful trajectory to learn about the magnetic field of the Earth.
Oh, okay. Hawkeye. I always think of MASH when I hear Hawkeye, but I'm from the TV show. Did you watch MASH?
No.
You must have watched MASH.
Well, before that, yes. Of course
slightly off topic here.
Well, okay. So I will admit, the very first date I went on is I took a young gal to the movie MASH. Okay, so
all right,
in the theaters.
Okay, let me ask you this. So we're a month now after Perseverance has landed. Where in the sort of pantheon of Mars exploration vehicles, how revolutionary is this one compared to something like the early Mariner missions, perhaps? I mean, obviously, we're looking in much more detail, much more sophisticated equipment, but how much of a sort of a paradigm shift or a quantum leap is this one, do you think?
Yeah, it is the next huge step in a line of strategies that NASA has been employing since the 60s. And it goes like this. For discovering things about our solar system, you first fly by. Check it out. Is this where we want to really look at more closely? Then you orbit. Then you land, you rove, and you return samples. So each and every one of those are huge paradigm shifts. And this one, Perseverance, is going to Mars to do exactly that last step. Create the samples we will return.
And where do you see it going next? So we've reached this step of collecting samples and depositing them. What's the next thing that's going to happen, do you think?
Well, we'll bore holes in rocks. So let me show you what one of these samples look like. Okay, so this was done with the engineering unit out at JPL. Okay,
is that one of the actual tubes or a model of one?
Yeah. No, this is the sample.
Can you hold it close to the camera so we can see?
Okay.
Yeah.
Okay,
Oh, I see.
okay.
So that's what it's like a piece of chalk. That's what we're going to get back.
Correct. Now the young people in the audience will probably not understand what you mean by a piece of chalk because they don't.
You mean young people like me?
Anymore. Yeah, people like you and I. So I have learned to call it, like a large Crayola crayon. Okay, so that's what it looks like. Then it's put in a sleeve. Okay, now this is a metal sleeve.
Oh, is that the sleeve? Or
yeah, this is the sleeve. Okay, this is the sleeve it'll go in. So it's sealed very tight. So any outgassing, so let's say the sample had some gases in it, trapped gases. Well, that happens all the time in samples, rock samples. Then in that sleeve, it will be sealed, and then that's laid on the surface of the planet for later pickup. Now, that's what's fantastic is indeed the next set of missions are all about retrieving those samples. So for the next couple years, Perseverance is going to run around Mars, creating samples and then laying them down on the ground. Then we're going to have a rover and a Mars ascent vehicle land on the surface of Mars. And the rover will run around and pick up those sample tubes. It's like picking up sticks. Now, a lot of the robotic contests that we do in NASA for kids are indeed building robots that can pick up, straws or various things. These are exactly the kind of things that, we're teaching kids right now in our robotic classes to do. So those samples will be then returned to the Mars ascent vehicle, put in a container, which will be mounted on top of the rocket, and then we blast off Mars. All right?
Yeah.
We'll then throw that container into orbit. So it'll be in orbit around Mars. Now, it'll be in a high enough orbit that it could stay there for years. But the next big mission is a mission that will go, get into orbit, hunt down that set of samples, retrieve them, pull out of orbit, and then bring them back and deliver them to this world.
So this is fantastic. 3 missions to bring back samples that are required.
And there's a lot of British European involvement in this as well, isn't there, Jim? This isn't just NASA. This is here as well.
Right. Yeah. So the European Space Agency, Canadian Space Agency, the UK Space Agency, many groups are getting involved, and they are really working well together to create this series of missions to return these samples.
So I'm really interested in kind of what happens when you bring them back, because I'm aware, they've come from Mars. We don't know what's in them. We're all very excited about what they might contain. What do we do next? We don't just open them up in our sitting room and have a look at what's in them.
Correct. You don't just open them up, because not only do they may have gases in the tubes, okay, but we don't know enough about Mars to determine if it actually has life there or not, whether it's past life or current life. So our approach is through a set of international guidelines we call Planetary Protection. So when we bring the samples back, they will go into a very secure facility. One of the highest rated facilities, many of these governments have developed. Some of these facilities, manage anthrax and various other types of viruses and problem systems. And so we want to be able to leverage those, quarantine them, and then methodically open them, examine them, do initial testing, and then hopefully they'll be released. But while they're even in the bio level 4 facility, we will be analyzing them. We will be taking samples, and we'll have machines there that will really tease out the mineralogy, the composition, and age date it. So when you core a rock, that's pages of the history of a planet laid down over millions and millions of years. So we want to read that book. We want to read those samples. So that's what will be going on.
What's the difference in terms of quality between something like these return samples and say a Martian meteorite? Because we do find bits of Mars on Earth, which is to me mind-boggling and ridiculous that I mean, you'll remember that in the 1990s there was a famous Martian meteorite, the Allen Hills meteorite, and they thought they found a little fossilized worm or bacteria, and we all got terribly excited.
Correct.
I can't remember how that story ended. Everyone thought, oh, it isn't a worm, and then someone thought, oh, it is a worm. And
that was a very seminal event in what we call astrobiology, the field of astrobiology, the field of looking for life beyond Earth. All right. And the reason why is it may have been the first indication that life could actually have occurred beyond our Earth, on another planet, in another object. So that indeed was a very important sample. Now, where we got that sample was the Antarctic. So we go down to Antarctica every summer. We get in snowmobiles and we move across the ice. Blinding white ice, glacier ice. And all of a sudden there'll be a black spot there. Okay, well, where did that come from? It came from above, right?
It's not like they specifically fall on Antarctica. It's just they show up best in Antarctica.
Samples fall on Earth every day. We estimate that there's about 100 tons of material, extraterrestrial material, that fall on this Earth every day. Okay, so you could go out to your yard and find them. If you knew what to look for.
A few weeks ago, there were some people in Cheltenham in the UK in a field, and they thought it looked like some cow poo, but it turned out not to be cow poo.
Somebody found one in their driveway, it just deposited a meteorite in their driveway. But answer me this. I have a question for you. Firstly, sign me up for the trip to Antarctica to hunt for the meteorites. I'm totally in. Secondly, they're dark in color, so when they land, they're visible. But do they melt the ice around them as they warm up? They're presumably, a lot of them are metallic, so they would warm up. And do they melt through the ice, or do they stay sort of on the surface?
Yeah, some will do that, depending on where they end up and what their composition is. Many of these are at a size that as they come in, they heat up and then explode. So then pieces fall all over the place. So the exterior of a meteorite is black. It's literally melted rock, okay? And so then that falls on the ice, but the ice isn't stable in the sense that it's not staying exactly there. It moves, and so that material actually will move with it. And some of these will fall on in the highlands, for which then, as the glacier moves, they will move down to where the rest of the ice is, and they will end up coming out and rolling around and laying on the surface. So when you look at one of these, what you see is a very dark, black, melted rock on the outside, and we call that the fusion crust. So here is one right here.
Wow.
All right.
Is that a bit of Mars?
Yeah. No, it's not Mars. I wish it was.
We're not interested there. We only want Mars.
But it could have been.
Okay.
All right. So here it is. So there's the black outside. All right. That's the fusion crust. Yep. On the inside, it's very different. It's grays and whites, and you see these whitey patches. Those are called chondrules. Those are some of the original early solar system material coming together, forming little dust particles that then end up forming a larger matrix as the whole rock gets together. Now, this turns out to be a meteorite from Chelyabinsk, all right, which came in. It was about 17 meters in size. I mean, bigger than a house. Can you 17 meters? All right. And as it was plowing into the atmosphere, it exploded. And of course, when we knew it was coming in, was way too late to warn anyone, because it was coming from a direction that wasn't on the night side where we could detect it early. It's coming in from the day side. And so the explosion surprised everyone. Many people got hurt, but they were all not, maybe superficial but no one died. And therefore, scientists were all over the place, picking up the material, bringing it together to determine what is it? Where did it come from? Now that one, it turns out, came from the normal meteoric population, which eventually was formed, we think, in the asteroid belt and then moved inward. And so it finally came to Earth orbit and we scooped it up. So these things can be found. You don't have to go to the Antarctic to find them. But when you do, every summer, we'll find anywhere from several hundred to 600 or 900 of these objects, bring them back to the laboratory. And then there's a very small percentage will be the moon or places like Mars.
But presumably those samples you find from the moon or Mars will have been contaminated by the Earth, so therefore they're not as desirable as a sample return in a hermetically sealed.
Yeah, so they could be laying on the surface of the Earth before we find them for millions to hundreds of millions of years. Okay. So when we got this particular Mars rock, we only had in our archive 11 more of these.
Wow.
So it was found at a time when we just started that process. All right. And then broke it open and then began to learn, is it Mars? Well, yeah, we found out it was Mars because the trapped gases inside it were the exact percentage of the gases that the Viking landers measured a couple decades earlier, all right, from the surface of Mars. So we knew that it was not really old, but definitely from Mars. And so we needed to date it, we needed to take it apart, needed to look at it. And that's where they started to see features that looked like fossilized microbes. Now, because it sat on the Earth all this time, microbes on Earth, water on Earth, invades these specimens and then alters their mineralogy, alters them in many different ways. And so that always caused doubts about whether this was really a Martian microbe or not. So this tells you right off the bat that what we need when we get samples is to know where they come from exactly. Not any old place on Mars, but exactly where they're coming from. And that's what Perseverance is doing. Boring holes in the rocks, taking images all around, shooting a laser down in the hole that it made, and getting composition and other materials that we then also gather that information, and it becomes part of the specimen, part of the information about the specimen for further analysis. And then it will roll around, and we're looking for it to, do maybe 25, 30 of these cores before we bring them back.
That's unbelievable.
And how far will it get? I'm interested in how far this thing is going to travel in its lifetime. What's our expectation for that?
Well, Curiosity, which is a similar rover. It has the similar look about it. It's also a 1-ton rover, that's been on the surface since 2012. And it's working great, wonderfully. And so there's no reason to think it won't have another decade worth of work to do. And Curiosity has gone well over 20 kilometers. So, it's nearly done with its first marathon. Okay, 26 kilometers.
It's quite slow.
Yeah, it takes a while.
That's about my pace.
All right, okay. So here's how fast they go. You ready? Top speed. It's flying. See that?
It's slow and steady.
There it goes. Now, why is it going so slow? Well, because we don't joystick it. We have to program it. We have to say, hey, this is where we want to go. And in some cases, the software on board is smart enough to figure out, well, I need to make these little adjustments along the way. And so consequently, it goes slow enough that if it gets into trouble, one, it has the opportunity to recognize it. Two, then stop moving. And then three, send back a signal, I need help. Then we'll get involved. Then our operators will see what's happening and figure out what's going on, make an adjustment, maybe pull it back and then move around a particular area, and off we go.
I've got to ask you, Jim, knowing what you know, having been at NASA for so long and having worked with, not that long. I didn't mean it that long, but for a while. But having worked with such extraordinary scientists, do you think we're going to get something interesting back from the Mars sample returns? Do you think? And like, if you had to sort of,
I think something interesting. I think they'll get something.
Okay, not something interesting, but are we going to get a positive past life result? I guess is what I mean. I mean, this is a biological mission, so
yeah. So looking for signatures of ancient life in rocks that you have in your hand is far preferable than trying to build an instrument that you can't anticipate what the life would look like or what it would be like, and put it on a small enough framework like a rover to do all that analysis. When these rocks come into a laboratory, it's going to be a huge room with all kinds of different analysis techniques that you could never, ever put on a particular mission. So what will we find? Well, it would be spectacular if we found some sort of indications of life. But whether we do or not, what we're going to learn is an enormous amount about Mars, not only its history, but also how it might be able to support humans for long periods of time, learning to live and work on another planet.
So the other thing I wanted to ask you about, actually, with regards to Perseverance, and that's really kind of captured people's imaginations, is your little helicopter.
Oh, yeah.
Everyone's sort of fascinated by this. So tell us a bit about what you're going to do with that helicopter and when it's going to fly and what the goals are.
Yeah. So Ingenuity is hitching a ride with Percy. So here's a little model.
Yes.
Nice.
All right. Okay. So Ingenuity is laying underneath the belly pan here. Okay. In a nice little tight container. When we decided we were going to actually fly Ingenuity, we didn't really know where we were going to put it, and we had it on the side in different places, and it turns out the belly pan works the best. All right. So right now it is folded up and it's tightly connected to the belly pan of the rover. And in a couple weeks, we actually, what we're doing right now is figuring out where the heliopad is, and we think we found a location. We're going to confirm that in the next few days.
What do you mean by heliopads?
Well, that's where we're going to drop the copter. It's
I see, like a little helipad.
Yeah.
Oh, nice. Okay.
Yeah, it's got to be flat.
With an H written on it. Like
it could, but we didn't bring the paint to do it. So we're going to roll over to the heliopad. All right. Yeah. Drop the copter and then pull away. The copter will unfurl. All right. Now, when we get about 50 meters back and we're ready to go, we'll send the signal to turn it on, and it will go through a series of tests. So the first test is really what we call just the up and down. So it will rise, 10 meters or so, stick around for a little bit, and then come straight down. Now, this is really an important test for the simple reason the first design of Integrity, the name of the helicopter, of course, is Integrity, in a chamber here on Earth, went right to the wall. That's not what we want. But we got it. We got to work on such that it can loft in that very thin atmosphere. And so we're going to test that. So I don't want to take it off. I want it to just go up and come straight down. That'll be the first test. Next test is it goes up a little higher. All right. And then makes a translation, parallel to the ground for another 10, 20 meters, and then comes right back. So it actually flies like an inverted L. Mm-hmm. So that'll be a really good test. All right. Then what we want to do is go back up again, over, down, such that it's an inverted U, mm-hmm. and then have it come straight back. All right, take off, come straight back. And that forms all the basic tests of rising, lowering, taking images, translation. And now we're ready for it to do a more difficult job, which would be to scout out an area that we would be planning to move Perseverance to or through. So we'll get high resolution images. The Ingenuity's got 2 cameras on it, one that looks out, one that looks down, okay? And that data will be stored on board and then transmitted to Perseverance, who then will hold that data until an orbiter flies over. And then we move the data off the Perseverance rover to the orbiter, and then the orbiter will send that back to Earth. That's how we get the data.
And are we going to be able to see these images from the helicopter when you see them? Are they going to be downloaded straight onto the website not in real time, but at the same time you guys get them?
Yeah, as fast as we can do that. That is indeed our plan. You know, we have what we call open data policy.
Yeah.
The things that we do, we want scientists all over the world to look at. And of course, we set it up such that now we have such a wonderful, you know, ability for the public to come along for the ride. I mean, how can you beat that? Let's find out what Perseverance is seeing today.
I think that's fantastic, actually. And I think the other thing about the landing, you know, many of us watched the landing kind of with bated breath. And one of the fantastic things was how quickly the images were available for us all to see. And I think that really kind of sparked imagination.
Yeah. I mean, I don't remember as a kid. I mean, I was born in the middle of Apollo. My big first space event was the landing of the first STS-1, the first space shuttle. But I don't remember ever being excited about uncrewed missions, you know, or missions involving probes before.
Robotic missions.
You know, like this one and the MSL, you know, in 2012, they've really captured the imagination like never before. It's fantastic, and it's because of the science. Because the science is so fascinating and so
it's tremendously compelling science.
Yeah.
I mean, you know, what you may not know, because you didn't live in that era, I did, and that was in the 60s. NASA had more than 20 missions going to the moon. We had orbiters, we did flybys, we landed, we tested the soils that were there before humans landed in 1969. Well, why is that? Well, because humans are pretty precious, all right?
We're high maintenance as well. We need
yes, you have to feed them more than just electricity. and indeed, what we want to do is we want to be able to bring them back alive. We want to be able to have the experiences of what a human can do, which is just a tremendous advantage of thinking skills and deploying things and orienting things and things that are so hard to do with robotic missions. We've learned to do it, but it's still very hard to do. Humans provide an enormous advantage. And so we want to learn, using planetary science, everything about an object before we send humans. And that, what we call, buys down our risk and then allows the greatest opportunity for humans to be able to contribute an enormous step, but do it safely in return.
We've got a couple of questions. We've got Megan, have we?
Hello.
Hi, Megan.
Hi, Megan.
Hi.
I can't. Oh, wait, there's Megan. There we go.
Can you hear me?
Yes.
It's the most common question on Zoom.
It really is that, and you're on mute.
Yeah.
We have to sell the Perseverance rover. You're on mute. Sorry.
Thank you for talking us through that. That was very interesting. My question is that you've had quite an extraordinary career. Do you have any personal highlights from your space missions that you've been involved with?
I have to tell you, every mission that I have been involved with, which is several dozen, there's been always spectacular moments. I mean, you know, the flyby of Pluto with New Horizons, the flyby of Arrokoth, a smaller object, a Pluto building block with New Horizons, Cassini's flybys of Enceladus that found huge walls of water going 150 kilometers and more into space. Now, I don't know how long you've been around here on Earth looking for walls of water that go up to space station, but there aren't any. I mean, these are spectacular.
Most of my days are spent looking for those.
Yes, I mean, these are just spectacular events. And then Titan. Okay, Titan's got an atmosphere. In fact, the atmospheric pressure on Titan is twice that of Earth's, and it's mostly nitrogen. It's a huge moon of Saturn. It is bigger than the planet Mercury. If we were to pull it out and have it orbit the sun, we'd call it a planet. I mean, you know, Cassini, in all the things that it did. Other missions like Dawn, which went out into the asteroid belt, orbited the two largest objects. One was Vesta, a beautiful object about 500 kilometers in size. Very different than many of the things that we thought about, that we found on this object. And then leaving Vesta, it went out to the outer reaches of the asteroid belt and got into orbit around Ceres. Ceres turned out to be twice the size of Vesta, but wasn't created, we believe, in the asteroid belt. It might actually be a Kuiper belt object like Pluto that came inward and was caught in the asteroid belt. Man, who would have thought of that, right? And then all our lunar missions, you know, we have, the Lunar Reconnaissance Orbiter is orbiting the moon right now. It can see the human tracks from the Apollo astronauts on the moon. It has this high resolution camera. All right, just a spectacular set of images. And I haven't talked about Mars yet. Think of all the, you know, fantastic missions we have at Mars. And then, of course, there's Mercury. We've been at Mercury.
You know, she's a Mercury, well, Mercury planetary
I
scientist.
spent 10 years studying messenger data, so I have to thank you for that.
Well, that's why I saved the best for last for you. Yes, I was aware of that. So, you know, I'm a magnetospheric physicist. All right. You know, that means that my specialty is magnetic fields, which means I you know, like any and all objects that have magnetic fields, and they're all over the place. Magnetic fields are a fundamental feature of our planets. And Mercury has its own magnetic field, its own magnetosphere, and it's fending off the solar wind. Mars used to have one. We don't know about Venus, but Venus probably did too. But Mars's magnetic field is gone. So what happened to it? We want to know about it. And so these are a lot of the open questions that we have now that our missions are going to be probing over the next many years.
The job that you did that made me most jealous was being a support diver in the neutral buoyancy tank with all the astronauts bobbing around underwater, and you were helping them as a diver. I think that's a brilliant job. Oh, I want to do that. How do I do that?
Well, I did it for about 5 years at the Marshall Space Flight Center. So that actually, when I started in NASA in 1980, okay, I was a scientist, you know, doing a lot of work on many different satellites, including the Voyagers, a lot of Earth's satellites. And I was at the University of Iowa, turned out to be a scuba diver. I just got into scuba diving, you know, so I dove in quarries, in rivers, you know, in places where the visibility is like 5 inches, all right? You know, some really slimy places. And I enjoyed that, you know, claustrophobia is not one of my problems, you know. So when I had an opportunity to get in the tank and be a NASA diver in this, you know, 70 foot across, 40 foot deep tank with a shuttle bay and all the stuff that they're planning astronauts to do, I thought I just got to get involved in that, and I had the opportunity to do that. So in those 5 years, I made about 150 dives.
Oh wow,
that's great.
Yeah,
that's great.
Neat.
There's a lot of opportunities, I think, for whatever you want to do in life. If you want to, you know, space science has it. Whatever you can do on Earth, I kind of think you can probably do in space in some degree.
Well, I find that, you know, being open for new ideas, new things is really critical. Yeah. I have what some people would call a character flaw, and that is I rarely, if ever, say no. So when opportunities come up, you know, where I'm asked to do things by NASA and get involved in certain activities, I never say no. You know?
That is a brilliant bit of advice for anybody who's watching. Never say no. I think that's. We had another question.
Firstly, Dr. Green, I want to say thank you for such an interesting talk. My question is that there are currently several robotic missions that are exploring Mars, and the first crewed Mars mission is expected to take place in the 2030s. How feasible do you think that it is that we will witness a human being successfully set foot on Mars within our lifetimes? And how feasible do you think it is that we are on track for our 2033 goal?
Okay, let me mention that I'm planning to be alive when we set foot on Mars. You know, I was alive when we stepped foot on the moon, and I have to tell you, with our current plans of going to the moon with humans, you know, in the next several years, our plans are to go to the southern hemisphere of the moon, have our first woman astronaut, and then maybe another woman astronaut, or certainly another man on the surface of the moon. That will be electric. You're really in for a treat, because I saw that with the Apollos. And so our plan is, in terms of using the moon, is to really learn to live and work on a planetary surface. The things that we're going to do on the moon are things that we will do on Mars. So the moon is going to be a practice ground for us. So the more we can do in that area, the more we can learn. And while we're developing the infrastructure to go to Mars, the better. So indeed, we have plans in the 2030s, 2040s for our first human missions to Mars. Okay, that's certainly in our lifetimes. All right, that's what we want to do. That's what we're moving towards. And in fact, if you don't, take time thinking about your future, you don't have a future. So we're going to be able to move those plans forward or back based on the kind of things that we learn on the moon and what we have to do to be able to learn and survive on the moon, which is a much more harsher environment than Mars, but looking for resources like water. One of the reasons why we're going to the South Pole of the moon has been some spectacular discoveries just in the last 5 or 6 years, that in the permanently shadowed regions of the moon might be several 100 million tons of frozen water, that these places have accumulated over time. Now, we can see some indications of that from orbit, from many different missions. Now we want to be able to go into those areas, create cores, ice cores. Those are the kind of things that we do in the Antarctic, creating ice cores, bring them out, look at the history of the moon through the ice core itself, and then, of course, melt it. Water is water. It's H2O, whether it's on Earth, on the moon, or on Mars, all right? We will drink the water. You can take the hydrogen and oxygen that make up water, break it apart, create rocket fuel, okay? You can take the oxygen and use it to breathe. So water is one of those fundamental resources that will be one of the first things we want to do on the moon, because that's the first thing we're going to do on Mars, is to be able to look at the water resources. Now, it turns out from some of the spectacular Mars missions, we think we've seen, under a burden of maybe several meters of material, we think we have found the ancient North Pole of Mars. Now, Mars's axis, not like Earth, it flips around a lot. And so during the past, the ancient North Pole was nowhere near where it is today. All right. And so we think we've found it. It's a huge location. It's bigger than England. All right. Some places, this ancient North Pole glacier may be 750 meters thick. So there's an enormous amount of water there. Now, we need more time to look. We need to look around, looking for groundwater, looking for other resources. And then we'll figure out where to land and then be able to interrogate those areas. Now, our plans for landing on Mars are not like the movie The Martian, okay? So we're not planning to go here one time and there and another, run around at these various Ares bases. We're going to land in one area. And in this area, we're going to call it an exploration zone. It's going to be about 200 kilometers in diameter. So we'll land in one area, we'll live in another area, and we'll grab resources that will be in this 200 kilometer circle. And we'll do that repeatedly for many, 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 many missions and build up this infrastructure before we move to another location. So you have some really exciting things in store for you.
Sounds good. We won't be growing potatoes in our own poo like in The Martian. That's the. Hey, listen, we're running out of time. Miranda, thank you very much, and Megan, thank you very much for your questions. It's been an absolute pleasure. Jim, it's such a treat to have you here with us today on our Mars Day. And I want to plug your podcast. You've got an amazing podcast. You plug your podcast for more exciting NASA science.
Well, what I really enjoy, scientists typically, as they go through their career, they're told by their advisors, well, you want to specialize, you want to know everything about one subject. That doesn't work for me. I love all kinds of science.
Me too.
Yeah, I just get so involved in that. And so fortunately, I've written papers all over the place in different areas. And that's been very important to me. And so I have run into some of the most spectacular scientists that hardly anyone knows about that have wonderful stories that where certain things happened to them that got them interested in becoming the scientists they are today. And I call that a gravity assist. And that's the name of the podcast.
Nice.
There we go.
How did you get into the science that you're doing now? Okay.
It's a brilliant podcast. If you sort of don't know quite what you want to do, have a listen to all these stories from different people, and you'll be amazed. It's terrific. I've been really enjoying it.
Well, thank you, Dallas.
We've run out of time. I think we've run out of time. But listen, we're gonna thank you, and we're going to be watching the Perseverance news with bated breath. We're looking forward to seeing all these images, and I shall be thinking of you every time I look at Mars from now on, and be wondering what Jim thinks.
My pleasure. Thank you so much for having me. It was a blast.
Thank you again.